Am I audible?
Yes, sir.
All right. All right. Before we start, I had put this post on the idea on the midsem. So those who are going to, uh, so how many of you are going to be participating in that? Have you thought about it?
Sir, can you explain the idea clearly? Okay.
See, the idea is that you will be given a topic. Okay. So the topic can be, for example, superconducting magnetic levitation, or it could be, let's say, hysteresis in type 2 superconductors. So in that topic, essentially it's the equivalent of doing a small term paper or a project. But here, since we are digital, we will, instead of doing it in a sort of in the form of a report that someone has to write, you will make it in the form of a video. So in the form of a video, when you record it, it could be just that, just like I give most of my lectures, you will be sitting there and deriving the stuff using either some pre-recorded thing on PowerPoint, or it could be on a tablet or whatever. Or you could do it more fancifully by including multimedia, videos, images, and so on. So, is the concept clear?
Yes, sir. But I have some. I want to point out something. There is some technical shortcomings from my side that, yeah, basically, as during the video recording, if I can do this in present in a form of presentation in a PowerPoint presentation, will this be right? Or because as when you are going to when you are giving a lecture, then you are using a pen, a tablet, and a pen. But I don't have that, and that's why I can't use those things. Yeah.
So, that is exactly what I mentioned. That what we will use, how we will present the you, it has to be exposition of a topic. Okay, how you are going to expose it depends on two things: how you think it will be best explained, and secondly is what are the technical facilities available with you. Of course, if you don't have a pen tablet, you will not use a pen tablet, you will use a PowerPoint presentation. That's obvious, so that goes without saying. All right. Yeah. So I'd like to, and the other thing that I want to also, I would prefer, instead of all of you doing it individually, you can actually make small teams of not more than 3 people. So at most 3 people, it can be 2 people also, and do it together. Of course, if someone wants to do it individually, I also have no problem with that. So you can also do it individually. Okay, so I would suggest that you discuss this with your friends in the within the class. You discuss it among yourselves, and then you, if you find this idea attractive, then you go ahead and do it. I thought it will be a fun idea. If some of you find this too intimidating and you don't want to get into this, then for them we'll have a conventional exam as a backup. All right. So let me know by Friday what is your tentative thought on this.
Sir,
Sir, the topics will be
Yes.
provided by you, or we have the choice to choose that topics.
So topics, I will be providing a list of topics. I and Surajit and maybe even the other graders will be thinking and giving you a list of topics. If you want to do on a topic that is outside this, then you have to discuss with me, because there are these topics. They have to be carefully chosen. They have to be topics which are not trivial. They cannot be extremely simple where you just do use some words and make a presentation. On the other hand, it also cannot be very complicated, because very complicated things is where essentially no one understands anything, so one can just blurt out anything and go ahead. So, for example, if you want to do a project on, if you want to do a presentation on holographic superconductivity, I would possibly say no. If you have a reasonable topic, then you discuss and let us see whether it's a suitable topic for a presentation.
sir, do we have to say something, or we can also just do a presentation only, or we have to do both?
See, the point is, it's not a live presentation. You understand that this is a recorded video. In the recorded video, the subject that is given to you, the topic that is given to you, has to be explained well. Now,
Okay.
for that explanation, if you want to give a lecture and record it, that's fine. If you want to use a PowerPoint, that's fine. If you want to make movies, if you are very good with multimedia and you want to make movies and embed it in that, in JavaScript or whatever, and make a professional presentation, even that is fine. So I have no constraint on what format you are going to use. It's at the end a video. So you have to use the best possible format that you think you can handle. What
Okay.
I would insist is the following, that when I give you the topic, and this we can discuss once I have assigned topics to you, your presentation has to be rigorous. So if there is, for example, if someone had, for example, tunneling, then the derivation of tunneling has to be rigorously there. You cannot just qualitatively explain the thing and then go over to fancy videos. That is not what is allowed or desirable in this presentation. It has to be rigorous, and it also has to be understandable. Understandable, by which I mean it has to be understandable to your batchmates. So if you cannot explain to your peers, then you cannot explain to anyone. So, and possibly you cannot even explain it to yourself. So therefore, within these two conditions, how you make the video, what format you want to use is essentially limited only by your imagination. And I have no fixed format, and I would like you to use your imagination and do the video in the best possible way you can.
Okay, sir.
Okay. All right, let me start the class. Again, if you have further questions, feel free to write those questions on Facebook group. Feel free to ask me. So we can uh, figure out, and when individual topics are assigned, then also you can discuss with me and the graders on what are the reasonable things to put in. So for example, if there is a topic called Josephson Junction, now Josephson Junction is something that you can write a book on. So You don't want to have a presentation that will cover everything. But what has to be covered, at what level it has to be covered, what material should go in, what should not go in. If you have confusion, if you have a very clear idea in your mind what you want to put, go ahead and do it on your own. You can use your discretion. But if you are confused, come back and ask us on what you think we think is reasonable. And then we can discuss it. Okay. So with this, let me start today's lecture. And today we will do the last part of what we set out to do is that using BCS theory, show that J is proportional to A. So this simultaneously will prove zero resistance and will also prove perfect diamagnetism. Okay, this is the last bit, and for this last bit we have to do some electrodynamics. Now, for simplicity, we will do actually very low frequency electrodynamics. So in principle, you can use this BCS formalism, and we can do high frequency electrodynamics also. But right now I just want to prove London equation in the low frequency limit. So therefore I will restrict myself to low frequency electromagnetic response. Okay, in fact, the high frequency response, I would love if someone takes it as one of the presentation topics. All right, so here I have to find out the response of the superconductor to a electric or magnetic field. Now let us start with this. You know that if I have a magnetic field or a vector potential, then the momentum gets replaced by the momentum and the field momentum. So P gets replaced by P minus EA by C. Okay, here I am using CGS units. So now the Hamiltonian, the original Hamiltonian that I had was essentially I have started with a free particle Hamiltonian. So it is P squared by 2m. Now in this case, if I go in the linear limit, the perturbation part of the Hamiltonian here, when I have a magnetic field, if I call this H0, will be one by 2m P minus EA by C whole square minus P square by 2m. So this is actually the general Hamiltonian, and this is actually the classical thing. So it will become quantum mechanical once I put in the operators for P and so on. So I will calculate the linear response. The linear response means I will assume that A is small. So it is a small magnetic field, and therefore I will ignore all terms which are like E square by C square, A mod square, this kind of term, I will ignore them. So if I ignore that, then what I will get is minus twice M E by C into P dot A plus A dot P. Actually, I am not writing twice A dot P because when I have to do quantum mechanics, P actually is an operator. So therefore, this will be minus E by twice MC into P dot A plus A dot. All right, now you know also that P equal to minus I H cross grad in quantum mechanics. So therefore, the quantum mechanical Hamiltonian will become I E H cross, and this is the first quantized Hamiltonian. Remember, this is not the second quantized Hamiltonian yet. If I have n particles, then it will become psi I dot A plus A dot del I. Alright, this is my first quantized Hamiltonian. All of you have done this. You have done the quantum mechanical problem of particle in a magnetic field. Possibly many of you have also solved the Zeeman effect problem. But now what we have to do, we have to second quantize this, because we are doing everything in the second quantized formalism. And for that, you can let us first write A in terms of its Fourier component as usual. And then you have to apply the prescription that we have done in great detail to go from first quantized Hamiltonian to the second quantized Hamiltonian. This is an exercise that I leave for you. And if you do this correctly, what you will get for H prime in the second quantized, that is why I have the hat here, it is E H cross by twice MC KQ K dot A Q and then CK plus Q sigma dagger. Actually, here there should be also a sum over sigma and CK sigma. Good. Okay, this is the general Hamiltonian. However, what I want to do is to show you, is to actually get the London equation. So therefore, I will assume A to be spatially independent. So which means that the spatial variation of A, I will take it to be very weak. I have a uniform magnetic field if you want, and therefore what I will take is A to be equal to AQ equal to 0. So then this, for uniform field, then I will get this perturbation part of the Hamiltonian to be twice EH cross by twice MC K sigma K dot A and Ck sigma dagger Ck sigma. Okay, so in the presence of a magnetic field, this is the perturbation part of the Hamiltonian. The remaining part, so the total Hamiltonian, of course, the total Hamiltonian will have the unperturbed part plus this part. Alright, so this will be the solution of this Hamiltonian will give me the effect of the magnetic field. We will come back to this again later. But now, let us find out what is the current J. Because if I have to prove J proportional to A, so what is J? Okay, for J, you know that J is equal to N E into velocity. N is the density, E is the charge, and V is the velocity of the charge. Now I know that P equal to mv plus EA by C, and therefore if I combine these two, then what I will get is J will become, let me see what it will become. Okay. So V is equal to 1 by M into P minus EA by C. So then J will be NE by M into here I will have P minus EA by C. Good.
Sir, sir.
Yeah.
So why you write P equal to mv plus EA by C? Is this because this charge is negative, or
Why do I write
P equal to mv plus EA by C? I mean, it should be P minus EA by C, right? So why this plus?
Let me
This
see.
is a momentum.
Yeah, P minus EA by C, that is what is equal to MV. So therefore, when you write the other way around, it becomes P equal to MV plus EA by C.
Oh, okay, okay.
Okay. All right. Okay. So now you see, I have two
Sir, I
parts.
have a doubt, sir.
Yeah.
Can you say that why we are using EA by C? Are we concerned about the motion of the electrons only?
What else?
Isn't it the pair of the electrons or something like that?
Oh yeah, yeah. So pair of electrons that will come in. We'll see. Ultimately, you have electrons. So you can write in general, and then you can have two electrons that will be. Means you can have that will actually come in what you take as N and E. Okay. Right now, I am just deriving the general equation for the electronic path. We'll see how it comes around. Okay.
Okay.
Means you can, it doesn't really matter. You can work either in terms of electrons or in terms of the Cooper pairs. But when it comes to penetration depth, actually it will not matter, because if you remember what is lambda square. Lambda square, if I take CGS unit, it is mc square by 4 pi ns e square. Now, whether you are working with one electron or two electrons, it will remain the same, because if you are working with one electron, this is m is one electron mass, e is one electron mass, and ns is the electron density. All right. So now on the other hand, if you take Cooper pair, then m becomes twice electron mass, e becomes twice electron mass, so you get 4 here. But then the density of Cooper pair is half the density of the electron, so that 2 cancels. So actually this remains exactly the same. So in the case of when you are calculating penetration depth, it doesn't matter whether you have Cooper pair or you have normal electrons. Means rather, that's not a correct statement. It doesn't matter whether your charge is 1e or 2e. It will remain the same.
Okay, sir.
All right. So now here you see you have two terms. The first term is NEP by M, and the second term is NE square A, is that right, by MC. All right. Now you see, if I had only this term, then I would have gotten London equation. So this term I call it J2, and this term I call it J1. Now J2 is equal to minus N E square A by MC. And this will straight away give you the London equation. However, you have also J1, and this if J1 was not there, we would have a problem, because here J2, it depends here on the electron density. It is not the density of the superfluid. We know from two fluid model we have density of we have a density of superfluid and a density of normal fluid. But J2 depends only on the density of the normal fluid, sorry, J2 depends only on the total density. So we know that the density of electron can be divided into the density of the superfluid and the density of the normal fluid. But J2, what it has here is this total electron density, which means that this should be, if I had only J2 in the current, then superconductivity should exist actually at all temperatures, because N2 never changes in a solid, no matter at what temperature, sorry, not N2, N does not change in a solid, no matter at what temperature I have. Electrons do not get destroyed. Okay, so J1 then, it must be playing a very interesting role, because I have to show that J is proportional to A, but only in the superconducting state. Above the superconducting transition temperature Tc, that J proportional to A should vanish. So let us now work with this expression, which is J1. Okay, what is this expression J1? J1, I can write it as EH cross by M actually let me not write the H cross initially here. So I have E by M, and then I have this P. P is what? P is the total momentum. So if I have to calculate the total momentum, I have to calculate the momentum for electrons in various K states. So H cross K is the momentum of an electron that is in the K state. And then I have to multiply by the number operator, because that's the number of electrons in this K state. And this will be the sum. Any question here? Okay. No.
Yes, sir. Why we are taking that the P is commuting with the potential part?
Commuting. Where?
Yeah, basically there is a potential part, right? With the that is acting between the electron potential. That is VK.
Yeah, but where did you see that here? In whatever I have done, I have just written the J in terms
Yeah,
of.
I'm just trying to say that we are summing the individual electrons momentum, right, to
Yeah.
evaluate the, yeah. But will that be so easy? Because there is an interaction between the electrons also.
Yeah. So you consider that, let's say you and your friend are running. What is your total momentum? The momentum of your momentum and your friend's momentum. Now suppose you are holding hands and you are running. What will be the momentum? Total momentum, your momentum and your friend's momentum. Is the interaction changing anything?
Okay, sir. Okay. Okay.
Okay, just think in terms of absolute simple stuff. Don't get into, this is the danger of mathematical rigmarole. Simple things, just think them simply. Total momentum is the momentum of every individual particle summed over. Interaction, no interaction does not matter. Okay? When you calculate the total energy of the system, of course, interaction will come in. But why should it come in the momentum? Does momentum depend on potential energy in your classical mechanics? It does not, isn't it?
No, no, it's not.
So therefore, momentum has nothing to do with any potential. All right. The point is that what will be the momentum of my particle can depend on the potential. But that's a different thing. I am just saying right now, I am not calculating what is the occupancy of these CKs, how many electrons are there for what K. That is not what I am calculating here yet. I will calculate that later on. Right now, I am just writing the expression for J1, which is that the total moment. So, and here is total momentum. P is the sum of the momentum of all the individual electrons. That's
Sir,
all.
what I am saying, can these be the case for an potential which is velocity dependent? Because in that case, we can invert the invert these as a, we can invert this and we can write the momentum as a function of velocity also.
See, both the velocity dependent potential. Okay, I haven't thought of velocity dependent potential. But I don't think that this expression would get violated for any potential. In the problem that we are doing, we don't have a velocity dependent potential, but even for a velocity dependent potential, why should this change? Just go back to the simple problem of you and your friend running. Suppose the faster you run, the more tired you become, so you keep dragging your friend further to try to get some drag of the, you try to get some drag force from him. Will this expression change? That the total momentum will be your momentum plus your friend's momentum.
Okay, sir. Okay, okay. Doesn't.
Okay. No matter what you do, this will not change. Okay. Go back and think about it. Maybe I am missing something. Maybe you are correct. If you can think of a situation where it actually does, we can think of it further. But I don't see how. Okay. Now, this, however, I know that if I am dealing now with a superconductor, this is a general expression. But if I am dealing with a superconductor, then my elementary excitations, the excitations that will follow the Fermi-Dirac statistics are the Broglie bonds. So I have to write this in terms of the Broglie bond operators. This is something you have already done, so I will not do it again. I will write what you will get is gamma k0 dagger gamma k0 plus 1 minus gamma k1 dagger gamma k1. That is what you get. Now plug this in here. I'll take the H cross outside. Okay, let me straight away write the expression and see if you all agree with me. Is this correct? Is this a correct? Is this expression correct? Where did the one go? That's the question.
So that is zero from the momentum conservation as we are summing over the all states.
That's right. So this one will just drop because that will be summed over all k, and for every k I have a minus k, and therefore this sum is 0. All right, now you see this expression I could have just written again intuitively without doing the calculation. Here, for example, what is the total momentum? It's the momentum of the, so I am calculating the total current, and the total current is the current carried by the upspin electron plus the current carried by the downspin electron. In the case of a Broglie bond, remember, one of the Broglie bond is, so both the Broglie bonds are a mixture of electrons and holes, but they come as UK and VK and VK and UK. That's the difference. So you have the UK and VK which is interchanged when you are creating 0 and 1 kind of Broglie bond. which essentially means that one of the Broglie bond is electron-like and one of the Broglie bond is hole-like. So just take any given energy, you will see that in one of them you will have the whole part which has a larger amplitude than the electron part. In the other one you have the electron part which is larger in amplitude than the whole part. So therefore when you are calculating current, it comes as a negative because in one case the current is a positive current, the electron part, the other one which is the whole kind of Broglie bond will be carrying a current which is negative, and therefore the total current will be the 1 by 0 kind of Broglie bond minus the 1 by 1 kind of Broglie bond. All right. So now as usual, if I have to calculate the physical current and any temperature, then I have to calculate the thermal average of this. So I will have to calculate this is the Fermi-Dirac distribution for the 0 kind of Broglie bond, and this is the Fermi-Dirac distribution for the 1 kind of Broglie bond. Now, in 0 field, of course, if let's say A was equal to 0, if I had no magnetic field anywhere, then Fk0 and Fk1 would have been exactly identical. But what will happen when I have A which is non-zero? I have a magnetic field there. This is what I am trying to calculate. So to understand that, let us see what the magnetic field does on the Broglie bond. So we know that for the electron, the magnetic field, it causes Zeeman splitting. Now, similarly, we have to find out what is happening here in the case of Broglie bond. So in the case of Broglie bond, you know that the second quantized Hamiltonian that I have written before was EH minus EH cross by MC K dot A Ck sigma dagger, Ck sigma, provided the A does not have much of spatial variation. Again, I have to write this in terms of the Broglie bond operators if I have to know what happens for the Broglie bonds. So it is K here, K dot A, and then here I will again get this quantity here. Now you see again the 1 here, so when I sum this quantity, so I have used here again this K, sum of K dot A over all K's is 0 from symmetry of the Fermi sphere, symmetry of the Fermi surface. Okay, now what does this Hamiltonian mean in terms of the energy of the Broglie bond? You see, for the 0 kind of Broglie bond, the energy has actually decreased by this quantity, EH by MC K dot A. For the 1 kind of Broglie bond, the energy has actually increased. So which means that if the energy originally was 0 for both the 1 and 0 and 1 kind of Broglie bond, Now the zero kind of polygon has decreased its energy by EH cross by MCKA, and the one kind of polygon has increased its energy. So this is very much like Zeeman splitting if you want. But there is a difference. The difference is that in the case of Zeeman splitting, it is not dependent on K. Here this is K dependent, which means that if you want the dispersion relation, which was like this to start with, this is the energy axis and this is the K axis. Then it has shifted, in one case it has shifted like this, in the other case it has shifted like this. So it has shifted along the K axis and the resultant energy change is from that. So this is a different way of splitting the degeneracy of 0 and 1 when you apply magnetic field. The way you are splitting the degeneracy is not the same as what happens in the case of Zeeman splitting. All right, so now I know that in this Fk0 and Fk1, the difference is that the energy that comes in one case is E0 minus this quantity, whatever, I forgot what it was. Let me call this quantity as delta K. And on the other hand, in K1, it is E0 plus delta K. Okay, so now I had the expression for J1, which was EH cross by M summed over K Fk0 minus Fk1. I will bother only about this for the time being. So you know that I have already assumed that A is small. So therefore I can do a Taylor series expansion. All right. So then J1 becomes twice E squared H cross squared by n squared c summed over a dot k into k, and then I have del EF del EK. Okay, so finally I have something that I can calculate. But then calculating this is non-trivial. I have to calculate this sum here. And let me actually, since I will, what I will do is, let me divide the problem into shells. So I will first do this sum for a particular shell, a particular constant energy contour, which means the following. So I will take this contour, and this is a contour for where it's a spherical contour of K modulus. Okay, so K modulus is constant on that contour. So I have to sum over all K. I separate it into these shells, these spheres, and then I will sum over all the spheres. Is that clear? So essentially I am taking all the K's on one constant energy contours, and then I will be eventually summing over all the constant energy contours. All right, so when I am doing this sum over, let's say, one particular constant energy contour, let me calculate. So for this constant energy contour, this quantity will be the same, because this quantity depends on energy. And I know that for a constant energy contour, the energy is the same. So energy is constant here. Energy is constant on this contour. So therefore, I have to have a way to calculate this quantity here. How do I calculate that? So let me take this constant energy contour now. And let me take, let's say, A to be in a particular direction. So let's suppose this is A. All right. And then let me take this to be K vector. So first I calculate A dot K. So this will be A dot K, AK cos theta. All right. So now this is fine. Now I have to calculate this quantity A dot K into K. First, can any one of you tell me what will be the direction of A dot K into K? Now A dot K into K is a vector. It's no longer a scalar. A dot K is a scalar. But when I take A dot K into K, that's a vector. What is the direction of the vector?
It's along K, sir. Because A dot K is a scalar, so it doesn't have any direction. So it will be along K.
Yes, it will be along K. When I sum over the contour, When I sum over this blue surface,
It should give you 0 then, because all that we are taking opposite directions too.
tell me, think better.
If one thing we can do, we are averaging over the cos theta for all theta, and it will give you 0. In that case,
It will not give you 0.
okay,
Okay,
let me think.
take these vectors in this kind of pairs. You have one k here, corresponding to that you have another k here. Similarly, we will have
Is along A?
exactly along A. So you will have one here, correspondingly you have one here. So therefore, these two together will actually give you k cos theta, because the component which is perpendicular to A will vanish, and the component perpendicular to A is vanishing. All right. So therefore, the only component that is surviving is along A. And it will not be 0 because you have twice k. You have A dot k into k. So therefore, whenever you have essentially it's proportional to k square. All right. So therefore, this will become something like a k square cos square theta. Okay, because and of course I have this sum here. Because I have all the component, and this the direction of this will be along A, so I can put that as NA unit vector. Okay, good. So therefore now I have to do this sum over the Fermi surface. So if I have to sum this over the Fermi surface, then what will I get? Now I have written something which, yeah, over a sphere of radius kf, I will have to take this average, and this is now easy to do, and if you do it, what you will get is cos squared average over the sphere is 1/3, over a unit sphere is 1/3. Okay, so I can write it now. What I am doing is nothing profound in it, but I will write it in nice forms. I multiply by n here. N is the electron density. Then I write mc. What I have done is here I put this as EF. So h cos square kf square by m is h cos square kf square by twice m is EF, the Fermi energy. That is what I have put here. It will be clear in a moment why I am doing this circus. 1 minute. And then I will write it again. So here I am not doing anything, I am just multiplying and dividing terms so that I can write things in terms of known quantities. So 4 pi n e square by mc square, and then this becomes 4EF by 3n, n is the electron density, and then I have all right. I hope this is correct. Okay, now why did I write like this? So what is this quantity over here? Can no one recognize this quantity?
Penetration depth.
This is 1 by lambda square.
1 by lambda squared at 0 temperature, because I have n here,
Yeah.
the electron density, 1 by lambda square. But what is this quantity? For those who remember free electron model, what is this quantity in free electron theory? We have assumed free electron theory actually throughout, that is why. What is this quantity here? Okay, if you have forgotten, I suggest you go back and revise free electron theory. The density of states at Fermi level, we always take 0 as our convention for Fermi level, is 3n by 4EF. You can find it in any solid state book, so I suggest you go back and refresh your memory. All right, so this is very nice. So now I can sum over this. I can change this sum into an integral, and you know that when I change the sum into an integral, I have the density of states which comes, but the density of states will get cancelled by this density of states, so there will be no density of states there. So I will get C by 4 pi into 1 by lambda square, lambda 0 square, I'm sorry, and then this minus infinity to infinity minus del F del E and summed over d xi. You know that E is E squared is delta squared plus xi squared, and therefore you know that from this you can trivially show that del E del xi is xi by E. This is trivial, so I will not do it. You can do it yourself. So therefore, this thing will become C by 4 pi 1 by lambda 0 square, and then when I do this, when I change this integral, so I will do a change of variable. Instead of d psi, I will keep here dE. But when I do dE, then minus infinity to infinity will become minus infinity to delta and then delta to infinity. But again, from particle hole symmetry, I know that the integral from minus infinity to delta and delta to infinity are identical. So I'll put a 2 and I will sum here delta to infinity. I'll just keep the positive one for simplicity. Okay. So this is my J2. No, sorry, this is J1. All right. What was J2? So this is J1. Is this J1 or have I dropped something in the middle? No, I did not drop anything. So this is J1.
Sir, is the A is missing here?
Yeah, A is missing. I'm sorry. Where did I drop the A on the way? Too many things to keep. Yeah. A was here, so A would be here and A would be here. Yes. Thank you. So J2 on the other hand is minus n squared by MC, if I am not mistaken, into A. And then again, these I can write by doing this multiplication and division. So I won't do this. You can do it very trivially. This will be 1 by lambda 0 square into A. All right, now if we have J2 and we have J1, then we can get J. Because J is J1 plus J2. We have already shown actually superconductivity because both J1 and J2 are proportional to A, which means that J is proportional to A. But let's see if we can go a little bit further and get a little bit more of insight. So I get CA by 4 pi.
So there is an 1 by n0 factor, I guess.
No, there is not. When you convert sum to integral, you have a n0 that comes and that will get cancelled by this 1 by n0. By now we have done millions of sum to integral. You should not forget this anymore. Del F del E. Okay, good. So we have proven first J proportional to A. But that's not enough because J proportional to A is very good, but we know that it should not be J proportional to A for all temperatures, then it does not make sense. If J is proportional to A for all temperatures, then I never destroy superconductivity. I know that superconductivity, there is a transition temperature. So then let us see what happens at T equal to Tc. At T equal to Tc, I know that delta is 0. So if delta is 0, then this quantity is, this quantity is 1. This del F del E is the delta function. And actually, even if it is not a delta function, actually the sum is, the weight under it remains the same. So if delta equal to 0, then this quantity becomes 1. So this integral becomes half, because it is summing over half a delta function if you want, multiplied by 2, and therefore it's 1. Therefore, the supercurrent vanishes. So it is the supercurrent's property that J is proportional to A. Normal current, J is not proportional to A. It's proportional to del A del T. So the supercurrent vanishes at Tc. So far, so good. Any question?
Yes, sir.
Yes?
Sir, in J1, where there is integral from minus infinity to infinity,
Yeah.
we have considered the whole electron symmetry and taken the twice.
Yeah.
But we know that around Fermi level there is a small window over which the symmetry persists. So while we are taking from up to infinity, we cannot consider symmetry or.
No. So you okay. The reason we are taking infinity is an approximation. We should not take infinity. But then we have no problem in taking infinity because we have del F del E and it's a sharply peaked function. So at higher energy, that function will quickly go drop to 0. So actually you can take this integral up to h cross omega d. But then before you go to h cross omega d, the del F del E factor will make it so small that you lose nothing by taking up to infinity.
Okay.
Understood?
Yes.
All right. Now, good. Now, there is a further interpretation here, and this interpretation is extremely potent. So, J, in the case of what was that? London equation, what I had derived was J proportional to A, but if you remember correct, if you go back to your equations and see what we had derived is this. This was the lambda square, the actual penetration depth. This is the penetration depth at T equal to 0, which means that you can now get the temperature dependence of the penetration depth from this equation. All right, so gives me the temperature dependence of the penetration depth. And you can again, so you can see the limits. At t equal to 0, this integral becomes 0 because this is a delta function, very sharply peaked at 0 energy, but the integral is from delta, it starts from delta. So therefore you are missing the delta function and you don't have anything. So this integral is 0 at t equal to 0. At t equal to tc, this integral becomes half, so multiplied by 2 is 1. So 1 minus 1 is 0, which means that at tc, your penetration depth diverges to infinity. This is exactly what we would have expected, because there is no diamagnetism in the normal state. Okay, with this, we formally come to the end of BCS theory. So we went step by step and we have derived all the essential properties of BCS theory. So we now have a job well done. Well, it was a job well done by BCS. There is something further. We have gotten the BCS temperature dependence of the penetration depth, and as you get used to, this will be also an assignment problem. In the next assignment, you will have to calculate and plot the temperature dependence of 1 by lambda square. So remember that in superconductivity, the first numerical problem that I gave you is to find out the temperature dependence of delta. Now then the second problem is the temperature dependence of specific heat, and when you calculate the temperature dependence of specific heat, remember you have to use the result of the first equation of the first problem, because you have to use the temperature dependence of delta, plug it in and get the temperature dependence of the specific heat. Similarly for the penetration depth, if you have to calculate, you have this delta here. And this delta is temperature dependent. So you have to plug in the temperature dependence of this delta into this equation here and here in both these places in order to get the temperature dependence of the penetration depth. Okay, so we end here, and in the next class we will take up some fun topics. We'll see. I haven't decided which one, but we will complete some of these intricate aspects of the superconducting state, whatever we have got from BCS theory. And from next week onwards, we'll start with the real space formulation of BCS theory, which is the Bogoliubov-Deussen equation. Okay, so I stop here. Questions?
Sir, I want to point out something about the slides. Am I audible, sir?
Yeah.
Yeah, so in the expression of the temperature dependence of penetration depth inside the integral, it will be E by root over E square minus delta square, not E square, sir.
Yeah, in this expression that you are
Yes,
seeing
sir.
now.
Yes, sir.
What is that?
It will be within the integral sign. It will be it will be E by root over E square minus delta square, not E square.
Oh, I see. Yeah, you are correct. Yeah, it cannot be square because then so it was from here that this mistake started.
Yes, sir.
Okay, let's correct this. Yeah, that is right. Am I audible? Something does not seem right here.
Yes, sir. You are audible.
Okay. Okay, any other question? Okay, if there are no other question, then let me log off here and we'll meet again on Friday.